The Calutron secret. How WWII engineers used 14,700 tons of Treasury silver for uranium separation. The request entered the government building on a humid Washington morning in a plain envelope that looked too thin to carry anything important. Inside it lay a single sheet, capable of derailing half the nation's wartime economy. The paper didn't specify a weapon, a laboratory, or even a project name. It contained only one line, an urgent demand for a quantity of precious metal so large that no financial analyst, no banker, no wartime procurement officer could make sense of it. The number exceeded everything the Treasury had ever moved in a single operation. It surpassed the reserves of several countries. And it came from an engineering division few Americans even knew existed. The men reviewing the request understood its scale before they understood its purpose. They knew the front lines consumed steel, aluminum, copper, fuel, rubber. They knew the aviation program devoured every scrap of electrical wiring the nation could produce. They knew the shipyards on the coasts were fighting daily for access to conductive materials. Yet nothing in the entire military supply chain explained why an anonymous installation under the War Department now demanded a volume of metal normally measured in years of national mining output. The request did not mention what the metal would become. It did not say where it would go. It offered no blueprint, no dimensions, no technical justification. But it carried the signature of an engineer whose authority inside the Manhattan Engineer District was growing fast, and whose reputation for quiet, uncomfortable urgency meant the paperwork would not be ignored. Outside the Treasury walls, America was straining under the weight of a war fought on two oceans. The country was rationing gasoline, restricting civilian automobile production, and diverting every major industrial plant into military use. Factories that once made household appliances now produced bomb fuses. Copper telephone lines were being stripped from rural counties to supply naval yards. Civilian construction projects were being shut down mid-frame because every pipe, cable, and fitting had been redirected to aircraft factories. There was no slack left in the system. No secret warehouse filled with unused materials. No backup supply chain waiting to be activated. Every ingot, every spool, every bolt was allocated, counted, scheduled, and reassigned before it existed. And then came a demand for an amount of silver so vast that even assigning trains to transport it would distort wartime logistics. Silver was not a typical industrial metal. It was a monetary backbone, a strategic reserve, a national symbol of stability in an era of global collapse. It sat in fortified vaults under layers of concrete and armed protection, guarded like a second heart of the American financial system. The engineers requesting it were not weapon designers in the traditional sense. They didn't build guns, tanks, or aircraft engines. They had been handed a scientific contradiction: to separate two nearly identical forms of uranium, one common and one capable of ending the war, on a scale no laboratory on Earth had ever approached. Chemistry couldn't do it. Mechanics couldn't do it. The known industrial techniques couldn't do it. They were left with a concept so oversized, so power-hungry, that its success depended on constructing magnetic structures larger than any built in human history. These magnets needed conductive windings of staggering length and purity. Copper would have been ideal, but copper had vanished from the American economy long before the request reached the Treasury. Mines couldn't keep up. Allocation boards were overwhelmed. Electrical manufacturers were begging the War Production Board for tolerances so thin they were almost theoretical. The engineers watched the copper reports collapse month after month until they finally concluded that no refinement of process, no negotiation, and no rationing order could produce what they needed. Only one metal left the slightest possibility of meeting the electrical requirements. Only one metal existed in the necessary purity, in the necessary volume, within a single guarded location. The engineers calculated the tonnage. The number looked absurd, a mistake, a misprint. It was not. The paper lay on the Treasury desk like a threat disguised as a question. To deny it would jeopardize a classified program already consuming billions in emergency funding. To approve it would mean melting down a portion of the nation's monetary foundation, reshaping it into forms no mint or bank had ever imagined. The request moved upward through the building, gathering weight and consequences as it climbed. Officials who understood economics recoiled. Officials who understood war hesitated. Officials who understood secrecy recognized that the true meaning of the request was hidden far beneath the text, in laboratories and machine shops the public would not hear about for decades. By the time the paperwork reached the highest level authorized to evaluate it, one fact had become clear. Whatever was happening behind the fences of that unnamed engineering district, it was so critical that even the country's financial stability could be temporarily sacrificed. What no one in that building yet knew was that this was only the beginning. The first shipment of silver would not satisfy the demand. The machines being assembled miles away would consume metal faster than the government could approve it. Engineers would soon discover that the initial calculation was not large enough, not ambitious enough, not remotely close to the true cost of building a device capable of rewriting the physics of warfare. And the next set of numbers, waiting to cross those same desks, would make the first request look almost conservative. A single fact turned possibility into obsession. Natural uranium contains only a whisper of the material that can drive a runaway chain reaction. That whisper, measured at 0.72%, is uranium-235, a brittle sliver of difference in a sea of useless mass. The rest is uranium-238, nearly identical in chemistry, indistinguishable by any practical reagent, separable only by the faintest difference in mass, 3 neutrons. Turning that whisper into a blast required moving mountains of metal, not by brute force, but by an engineering scalpel that could detect and isolate atoms by weight. The scale of that task is easy to underestimate until one translates percentages into the cargo manifest of a weapon. To assemble a device, scientists calculated you needed material enriched to roughly 90%. From a feedstock that was nearly all heavier isotope, the arithmetic was unforgiving. The quest to split isotopes had begun earlier in the century, in laboratories where curiosity met crude tools. Mass spectrometers existed as delicate instruments that separated charged particles along slight curves in magnetic fields, resolving molecular fingerprints for chemists and physicists. Those devices handled milligrams, micrograms, sometimes less. They were precision toys. The war changed the goal from analysis to production. Laboratories could show that isotopic separation was real. They could not show how to manufacture tons of enriched uranium in months rather than decades. Every proposed method bore an impossible tax. Gaseous diffusion demanded membranes that did not exist at the scale required, huge cascades of stages consuming energy like an industrial furnace. Thermal diffusion required enormous arrays and consumed power while delivering low yields. Centrifuges promised elegance, but demanded rotors that would spin without disintegrating under colossal centripetal forces. Manufacturing tolerances were tighter than wartime factories could sustain. Each route presented engineering gaps that mapped onto supply chains already strained by armaments, shipbuilding, and civilian needs. The problem was not purely theoretical. It was inventory and logistics dressed in equations. The urgency multiplied beyond simple wartime haste. Allied intelligence and the fog of incomplete reports suggested adversaries might be progressing on parallel tracks. Silence from laboratories in Europe, refugees carrying fragmented reports, and intercepted cables fed a climate of strategic dread. Scientific committees, military planners, and political leaders slid closer to one another in a high-stakes geometry where a single misread calculation could cost millions of lives. Funding flowed with a new velocity. Bureaucratic caution yielded to experimental license. Yet license without feasibility was a hollow thing. Amid this environment, a handful of researchers returned to a principle that had long been tucked in the back of spectrometer manuals. Charged particles deflect in magnetic fields according to their mass-to-charge ratio. Scale that principle by many orders of magnitude, and the laboratory trick begins to look like industrial potential. Conceptually, it was simple. Practically, it was monstrous. The device would need to ionize uranium atoms, accelerate them, hold them in an evacuated path, and bend their trajectories with magnets vast enough to make tiny differences in mass translate into spatial separation, measurable by collectors. The vacuum chambers, the ion sources, the magnetic fields, all had to be not only large but exquisitely stable. Tests in university basements and campus machine shops produced promising traces, fractions of a microampere, an 18th of a microgram, enough to whisper that the physics would not betray them. But translating a whisper into a chorus required machines that would be heavier than the research teams that envisioned them. Magnets that needed conductors in quantities rivaling those used in entire municipal power grids, and tolerances that would crumble under thermal drift and mechanical creep. The vacuum systems would have to be maintained at pressures that industrial pumps of the time could barely sustain for small enclosures, let alone for rooms that might rival hangars. Engineers sketched apparatus that looked like cyclotrons grown into factories, and the drawings acquired a grim clarity. To separate significant amounts of material, they would need dozens, then hundreds, of such assemblies operating around the clock. Philosophical debates attended every technical contention. Some scientists argued for distributed approaches, dozens of smaller plants using parallel methods to avoid single points of failure. Others preferred concentration of effort on one potentially winning technique, rationalizing that resources would be easier to marshal if directed at a single, audacious design. The argument was not only about science, it was about trust. Trust in materials, in manufacturing capacity, and in the chain of people who could keep such fragile systems running under wartime strain. At the end of the year, the problem had ceased to be a paradox and had become a ledger of demands. It required a convergence of metallurgy, vacuum technology, electrical engineering, and logistics at a scale the country had rarely seen. There was no precedent for ordering thousands of tons of conductive metal for a single facility, no template for guarding and transporting bullion repurposed into industrial feedstock, and no social model for recruiting a workforce to operate gray boxes whose purpose could not be spoken aloud. The laboratory successes provided confidence that nature could be persuaded to cooperate. The rest was a question of industrial imagination. The demand for conductors rose faster than any forecast could capture. By the middle of 1942, the nation's industrial arteries were straining under an unprecedented surge of military production. Shipyards swallowed copper by the freight car load, aircraft factories rewired entire assembly lines each month, and ordnance plants consumed metal as if the war were feeding on raw elements themselves. Every available pound was already spoken for before it had even left a refinery. When the electromagnetic design team calculated how much copper the new separators would require, the answer overshadowed all prior shortages. The machines needed massive coils, each one built to endure fields far stronger than anything previously engineered. The final estimate reached a figure so large that procurement officers refused at first to believe it had been calculated correctly. The scale became clearer when logistics officers mapped the supply routes. Even if every commercial contract were canceled, every civilian industry stripped of its allocations, and every reserve tapped until warehouses stood empty, the total amount would still fall short. Copper was the metal that powered the war's electrical muscle, and the notion of diverting tens of thousands of pounds to an unproven device cut directly against every priority set by the War Production Board. Yet the electromagnetic design could not be altered without jeopardizing the entire enrichment strategy. Smaller coils would not generate the required field strength. Substitutions with inferior conductors risked catastrophic overheating. The scientists were caught between the physics of the process and the brutal arithmetic of wartime scarcity. In engineering reports stamped confidential, alternative materials were surveyed. Aluminum appeared promising on paper, but suffered from resistance limitations that would force the generators into unsafe overloads. Experimental alloys looked attractive in laboratory trials, yet collapsed during stress testing. Even repurposed industrial scrap, a desperate option entertained late one evening, failed to withstand the heat loads predicted for continuous operation. The list of viable metals dwindled until only two remained: copper, which no one could obtain, and another conductor that belonged not in a factory, but in a vault. The idea emerged during a routine comparison of conductivity values. Silver, long regarded as a monetary instrument rather than an industrial commodity, possessed electrical performance superior to copper by a narrow but critical margin. Under normal circumstances, such a substitution would have been dismissed as extravagant, but the circumstances were no longer normal. The war was reshaping the country's priorities, and the project's leaders understood that physics did not negotiate. If the coils were to function, they required a metal capable of carrying enormous currents without sagging or rupturing. Silver met that requirement. Nothing else did. The proposal arrived on the desk of the procurement director, accompanied by an analysis describing the extraordinary quantities required. The first reaction bordered on disbelief. The amount of bullion necessary for a single set of coils represented a significant fraction of the nation's strategic reserves. Every bar was intended to back currency or stabilize federal accounts during emergencies, not to be melted down and forced through industrial presses. Furthermore, the Treasury had never before released precious metal on such a scale for any wartime application. The precedent did not exist, the regulatory pathway was uncertain, and the political consequences were unpredictable. Engineers, however, were not dealing in politics. They were dealing with magnetic fields so intense that even minute deviations would compromise the entire enrichment chain. Calculations showed that silver's higher conductivity could reduce thermal losses enough to keep the separator stable at full power. In an operation already balanced on the edge of feasibility, even marginal performance gains had the weight of strategic necessity. The decision moved slowly at first, reviewed by officials who understood only fragments of the classified rationale. But as additional analyses arrived, the picture sharpened. Without an alternative metal, the electromagnetic method would stall before it produced its first measurable output. Without enrichment, the broader objective of securing a reliable fissile supply would collapse. The stakes were no longer industrial, they were geopolitical. Weeks passed in a haze of paperwork, coded memoranda, and closed-door briefings. Only a small circle grasped the enormity of what was being considered. Replacing copper with silver meant disassembling a portion of the nation's monetary foundation and transforming it into machinery never meant to last beyond the war. Risk multiplied at every stage. Transporting the bullion invited security vulnerabilities. Casting it into coils introduced the possibility of contamination or irreversible loss. And the public, if informed, might question why the government was melting wealth to pursue a technology whose success remained far from certain. Yet the analysis remained unchanged. There was no other path forward. While engineers refined their electromagnetic schematics and physicists continued to validate ion trajectories, the procurement division prepared a request that would redirect a breathtaking quantity of national assets into a single experimental facility, The moment the final document was signed, the enrichment project crossed a threshold from ambitious to unprecedented. The metal that once safeguarded the country's currency would soon become the backbone of a device intended to safeguard something far larger. As preparations advanced, a quiet realization spread among those closest to the project. The silver coils, once installed, would not merely represent an engineering solution. They would embody a wager placed by an entire nation, one that would either reshape the war or vanish into the machinery of an idea too bold to guarantee. The hunt for a replacement conductor began as an act of desperation, not innovation. By the time the engineers admitted that copper had become unattainable, the Manhattan Engineer District was already behind schedule, already overextended, already gambling its future on machinery that existed only on blueprints pinned to drafting boards. The electromagnetic concept demanded colossal coils, and coils of that scale needed a metal that could carry staggering electrical loads without collapsing under heat or warping under magnetic pressure. Copper was ideal, but copper in wartime America had become a battlefield currency more valuable than some weapons themselves. The Army Ordnance Department was claiming every available ton. Naval shipyards were stripping backlogs of it to produce wiring for destroyers, and factories turning out communication systems were surviving on ration cards and promises. The idea of acquiring thousands of tons for a single scientific project seemed delusional. Engineers began combing through technical archives, searching for alternatives. Aluminum appeared first on the list, but its conductivity lagged too far behind. Even enhanced alloys offered no salvation. The power losses alone would make the machines unusable. Experimental metals that laboratories had toyed with in the 1930s existed only in gram-level samples, not in quantities measured by trainloads. The problem was not simply finding another conductor. It was finding one that existed in the real world, in volumes comparable to a small mountain. That requirement eliminated nearly every industrial option. The development teams reviewed archives from mining associations, shipping manifests from the previous decade, even old federal procurement tables from the interwar years. Every path circled back to the same dead end. Nothing on Earth could replace copper at the scale the mission required. The breakthrough came not from physics, but from economics. A metallurgist studying conductivity tables noticed that one element surpassed copper by a narrow margin. It carried current with remarkable efficiency, resisted corrosion, and could be formed into the long, continuous strips that the coil designs demanded. It was also deeply impractical because it was not primarily used in factories or power stations. It served as currency, wealth, collateral, and reserve. Silver had been the backbone of monetary systems for centuries, stored not in warehouses, but in vaults hidden behind reinforced walls. No engineer would normally suggest melting it down for industrial coils, just as no accountant would propose using banknotes to insulate boilers. But the war had reached a stage where the unimaginable had to be weighed alongside the necessary. Once the material appeared on the shortlist, the consequences unfolded quickly. Engineers recalculated every specification of the coils, adjusting for the slightly different density and melting point. They estimated the tonnage required and realized that the figure exceeded anything available in commercial markets. Mines could not produce it fast enough. Private reserves were scattered and legally untouchable. Jewelry and silverware constituted an insignificant fraction. Only one source possessed enough metal to match the demand. The federal stockpile held under government lock. It was an option no one wanted to acknowledge because of what it implied. Borrowing that much precious metal would mean diverting national wealth into a machine still considered experimental. It meant turning a monetary asset into industrial scrap with the hope that it could someday be recovered. The engineers preparing the feasibility report understood the scale of what they were suggesting. The Federal Reserves stored silver by the tens of millions of ounces, guarded by protocols designed to withstand economic crises and national emergencies. Converting those carefully cast bars into billets and strips would break traditions older than the Treasury itself. Yet every other path had collapsed. Copper would never appear in the quantities needed, and without a conductor capable of surviving the electromagnetic fields, the separation plant would fail long before reaching operational capacity. The war was moving full speed across Europe and the Pacific, and the scientific project behind the scenes had no room for compromise. By the time the analysis reached the highest engineering offices, the conclusion was unambiguous. If the electromagnetic method was to stand a chance, the nation would have to sacrifice not only labor, materials, and secrecy, but a portion of the financial bedrock on which its currency rested. The decision would force the government into unfamiliar territory, blending national defense with monetary policy in a way that risked controversy long after the war ended. The recommendation stood on a single line in the final report, written without embellishment. Silver must replace copper. And in that moment, the technical challenge transformed into something far larger, because choosing that metal meant convincing the United States Treasury to surrender thousands of tons of wealth for a machine that had not yet proved it could function. The first shipments left the federal vaults before sunrise, moving under a level of quiet tension usually reserved for wartime gold evacuations. Yet these trains carried something even more symbolically volatile. They held the financial backbone of a nation at war. The metal inside those crates had once represented stability and permanence, a hedge against economic collapse. Now it was being pulled from concrete chambers and steel cages, loaded into rail cars, and sent into a manufacturing chain designed at a pace no proper engineer would ever endorse. The sheer volume of the withdrawn bullion reshaped entire procedures. Guards who had spent their careers patrolling quiet, chilly corridors suddenly found themselves escorting convoys across multiple states. Clerks accustomed to balancing accounts measured in ounces now had to reconcile inventories measured in thousands of tons. Every inch of paperwork had to be redone, every chain of custody form rewritten to reflect the unprecedented scale of this transfer. What had been a motionless reserve became a river of metal forced into motion by the pressure of global conflict. Once the bullion reached its first stop, the transformation began. The bars, each weighing roughly 30 kilograms, were no longer considered symbols of national wealth. They were treated like industrial feedstock, stacked like any other raw material, waiting for the violence of the furnace. Heat capable of warping steel beat against the silver, reducing the once polished surfaces into molten currents. The metal's gleam disappeared into a swirl of blinding white and deep orange. Workers who had handled metals their entire lives watched with disbelief as a resource normally measured with reverence dissolved under the weight of war. From the furnaces, the metal flowed into molds shaped for efficiency rather than elegance. Cylindrical billets emerged, still steaming, their surfaces marred by a texture that hinted at extreme temperatures and unforgiving deadlines. These billets traveled to the next facility, where the true brutality of the process unfolded. Silver, softer and more conductive than copper, moved through extrusion presses designed originally for another purpose. Enormous hydraulic forces drove the metal through precision dies, stretching and compressing it into long, narrow strips. Every stage introduced new risks. A misalignment in a die could destroy an entire batch, wasting metal worth more than small factories. A temperature variation of only a few degrees could create microscopic fractures, invisible to the eye, but devastating once installed in the final assembly. Supervisors documented every deviation, every vibration, every hint of stress in the production line. The metal had to be perfect, because nothing less could withstand the immense magnetic forces it would soon endure. The silver strips were then annealed, cleaned, inspected, and packed for transport to the next facility in the chain. As they cooled, their surfaces reflected harsh overhead lights, creating a sterile brilliance that contrasted sharply with the wealth they had once symbolized. Workers moved the finished strips into guarded rail cars, each load monitored with an accountability more rigid than most wartime weapons shipments. It was a strange paradox. This material was precious enough to warrant extraordinary surveillance, yet common enough in the manufacturing chain to be handled by dozens of people across multiple states. Each delivery traveled under strict watch, but not always in ways apparent to the public. Some shipments used decoys, others relied on timing and obscurity rather than armed patrols. The scale was too vast to guard every mile of track, and officials had to trust that the secrecy of the mission would protect it better than rifles. What mattered most was continuity. The chain could not stop. The furnaces could not cool. The extrusion presses could not sit idle. A single delay could set the entire schedule back, jeopardizing a wartime strategy built on precision and fear of losing ground. At every facility, workers signed compliance notices, acknowledging that any fragment of metal, lost, even a speck small enough to escape a fingernail, had to be reported. Floors were swept daily, and the sweepings collected like treasure. Filters were burned to recover invisible particles. Dust that would normally be discarded was instead cataloged and stored. The metal had been loaned, not gifted, and every ounce had to be accounted for. By the time the silver reached its final form, the scale of its metamorphosis defied imagination. What had once been stacked in near-silent vaults as a symbol of stability had become a lattice of industrial components destined for a project so immense and secretive that most of the people handling the material would never learn its purpose. The nation's wealth had been recast into the spine of a machine that had yet to prove it was even possible to operate. But as the final shipments left the factory and headed toward the construction site in Tennessee, engineers began receiving troubling reports. Something in the extrusion data hinted that a portion of the metal, under specific conditions, might behave unpredictably once subjected to sustained magnetic fields of unprecedented strength. No one yet understood whether the anomaly was a quirk of measurement or a warning of catastrophic failure waiting to happen. Construction at Oak Ridge advanced with a speed that defied ordinary engineering logic. What began as rough sketches and tentative land surveys grew into a landscape of steel frames, drainage ditches, rail spurs, and access roads stretching farther each week. By the early months following the silver shipments, the chosen valley was no longer a quiet patch of Tennessee woodland.